All right, guys, this is problem number 7 on the pink sheet homework that I'm making a video for, just to help folks who, some of my classes, we were able to do this model problem during class and some we were not able to. So I'm just gonna clean up the diagram. So this says we have a cylinder and it exists inside of a sphere, and the radius of that sphere is 5. So if you look at the diagram, that's what this segment here represents. So there's a few things we want to sort of look at here. We have this distance here, x, and this x ends up being half the height of this cylinder, because the way, if you sort of think about the way a cylinder would exist inside of a sphere, the center of the cylinder would also be the center of the sphere. And then up here we have this segment here. That's going to be the radius of the circular base of the cylinder. So I'm just going to sort of call that R for radius. And what I want to do is I want to think about expressing the volume of this cylinder in terms of X and R. We don't need to worry about the volume of the sphere because this 5 is what sort of anchors this cylinder to exist within that sphere. So the volume of a cylinder is going to be the area of the circular base. So area of a circle is pi r squared times the height of that cylinder. So you want to sort of make sure volume is 3 dimensions. So we have our 3 dimensions by squaring the r and then multiplying by h, where those are both variables. Pi, it looks like a variable, but it's a constant, so we're going to leave it alone. So what I'm going to do now is I'm going to keep my pi. I'm actually going to rewrite r in terms of x. I'm going to kind of leave a little space there, square it, and then multiply by height. Height is going to be 2x because this distance represents the distance from the center of the cylinder to the top. So 2x is going to be my height. Now we're going to sort of sidebar, and we're going to write an expression for the radius in terms of x by using the Pythagorean theorem. Sort of consider this to be a right triangle. So we have x squared plus r squared equals 5 squared, which is 25. Sorry, you can't actually see that in the video. There we go. If I were to solve each side for r squared, I would have 25 minus x squared. And so r squared equals 25 minus x squared. I could solve for r, again, by taking the square root of each side there. I don't need to do that because, as it turns out, the formula for the volume of a cylinder requires an r squared. So I'm actually solving for r squared and then plugging that back in. So I'm going to go back over here. Instead of squaring the r, I'm just replacing r squared, so this guy here, with 25 minus x squared. And that's going to give me the volume of the cylinder. Okay, so this, now we have our sort of think about pi as your coefficient, and we have a factor of 25 minus x squared, and we're going to have a factor of 2x. And from this point, what we want to do is we want to find the maximum volume by graphing this guy in Desmos. So in Desmos, we're going to punch in, we can do, v of x, something like that, is pi times 25 minus x squared, wrap that up, my other factor of 2x, and we're going to end up with a negative cubic function that's going to look something like this. And we are going to have a local maximum point here. And the coordinates of that point are going to be x and v of x. So the x coordinate is this input here, so half the height, and the output is going to be the maximum volume. And we've sort of talked about why this turning point is so crucial and what happens when we have a piece where, there are obviously values on the function that exist that are more maximum than this turning point, but they will not work in terms of the context of the problem where every dimension has to be positive and has to be restricted based on, existing in this sphere. All right, so just to show you guys how this looks when we actually graph it in Desmos. So I've plugged in those factors with the pi, so there's our function to consider volume of this cylinder. You can see the scale on this coordinate plane isn't working so great for us, so I'm gonna just adjust the settings. I wanna see a lot less X. So I'm looking here, I'm thinking maybe like -5, that was not correct, maybe -5 to +5. And here we'll do +5, and that kind of cleans that up for us a little bit more. Now I can really zoom out and I can look at this maximum value here. And Desmos knows that we're looking for the maximum value. So this is the X value, so the half the height, that's going to give us the maximum volume of that cylinder, and then this number here is the maximum volume of that cylinder.